Okay, so we're going to do inverse of a quadratic function. This is a quadratic function. Now, I know you're used to seeing maybe a parent function. And what they mean by a parent function is something like this, where they'll have a. Let me just put the rest in. So you'll have something like this. A, which is essentially our 2 here. Now, do you guys use h as a variable there?
Yeah, but a height, right?
That will go moving a parabola left and right, and this should be a plus sign. And then k on the outside. You guys might use different variables. Sometimes maybe this will be a c and a d.
No.
They use h and k? Okay, great. So h deals with moving a parabola left and right. K deals with moving it up and down. A is stretching it vertically. But what's important is you notice that right now this is called vertex form. Okay? And they call it vertex form because it's really easy to see where the vertex is. This is going to be the y value of the vertex, our k value.
Yeah.
So if I wanted to write down the vertex of this function, right, so I have my x and my y value of what that point is. The k is exactly what the y value is going to be, -4. And now I'm talking about the entire thing here of our h, so +3, it'll be the opposite of that for our x of the variable, so it'll be -3. Yeah, so that will be where the vertex is.
So it has nothing to do with the 2 on the outside of the square?
No. Square, well, the square tells you it's a quadratic, okay? And the 2 is going to tell you that it's actually going to be very thin compared to a normal one. But in terms of vertex, because they call this vertex form, okay? And the reason they call it vertex form is because you can look at it easily, right? This is vertex form, and you can see exactly where the vertex is going to be, okay? So that's just a side note. Now, what we're really trying to get into is an inverse of a function. Now, when you're going to graph this, we have this function. And what is this function, when you're going to graph, essentially stands for our y. Okay? What it's saying is the function with the variable x is represented by this. Great. So what we can do in this is we can replace our f with y. And we still have the same function. Okay? Exact same thing. And we use x and y because on a graph we use x and y for the axes, right? So if we were to sketch a quick graph, we have our 2 planes, x and y plane, right? And that's why they use x and y equation. Now, an inverse of a function, what they're actually doing is they're taking the y and the x and they're switching the 2 of them. So whatever place they are in, this will now become the inverse of the function. So what now happens is we get x in place of the y is equal to, everything else stays the exact same. Y goes in place of the x. And again, all the other numbers stay the exact same. Now, so this is how we start the inverse of a function. So we had our original one, and then we swapped the x and the y and what positions they were in the equation. What's important now is our goal is to get back to where we were. We used to run where just y by itself on this side. That's what we're trying to do. We need to get y by itself on this side. So when we're trying to isolate a variable, we do what's called, essentially, usually do things called reverse bedmass. Usually use bedmass in order to figure something out. Reverse bedmass is what we'd use the other way. So what that means is I'm going to deal with the addition and subtraction first. So I want to move -4 to the other side of the equation. Okay. So we move -4 over. Do you know what's going to become on the other side? Yeah. So x plus 4 is equal to 2. Y plus 3 squared. Okay. Again, reverse bedmass. The next thing we deal with is this. This means multiplication. 2 times whatever's in that bracket. So if I need to move the 2, what would I need to do? Well, it is multiplication, so in order to move it to the other side, yeah, exactly. So technically, we would divide both sides by the number 2. So now we're left with x plus 4 divided by 2. These two, they say they cancel out, but really what happens is they create a number 1. And the 1s doesn't change anything, right? But that's why they'll say it cancels out a lot of times. It really creates a 1. Anyways, then we're left with bracket y plus 3 squared. Again, the goal is to isolate our y. So instead
of you do the square root
exactly
of both sides?
Yeah, exactly. We're going to square root both sides. Okay. And again, these will, they say, cancel out. They create a 1, but we're left with the root of x plus 4 divided by 2 is equal to y plus 3. Now, I don't need these brackets anymore. They're not very important. So last thing I need to do is now move this 3 to the other side of the equation. When I move 3 to the other side of the equation, what's it going to become? Exactly. So we're going to end up with y is equal to, which was exactly our goal, the square root of x plus 4 divided by 2, and then outside of it, yeah, minus 3.
So would you put brackets over the?
You could put brackets around it if you want, but no, this is just, what this is you would equate this part first. So say we had the number 1 in here, we'd have 1 plus 4 is 5 divided by 2, then we'd square root it, and then whatever that number is, we'd subtract it by 3 in terms of order. Okay? So, this is everything we went over. That's the steps to inverting a function. Okay? Now, this function is going to be an inverse on a graph, and when they talk about that is we say we had a parabola like that, it's going to look something like this. And what that means is we're flipping it on a 45-degree angle. Let's see if I can get that.
And how? Okay, so we got the. We
So-
started with y and then we ended up with the same.
Yeah,
So
Exactly. So we started with a quadratic equation. Quadratic is when the x variable is squared. So the original of that usually looks like this. Y is equal to x squared. That's what we're talking about. That's what the normal one is.
Yeah.
Okay.
Can we go over that after too?
Yeah, of course. Right. So that's what the normal one is. And now what we got is a root function, which is, you could say a sideways parabola, but it depends if they want us to keep it as a function or not. Sometimes they'll only draw it as half of a parabola and not the other half. And we'll go into graphing that in a second. Okay, so the other thing they're going to want you to do, there's 2 other points we should recognize, okay? So they want you to write it back in function notation. In other words, they no longer want this equal to y. They want it equal to f at x, okay? But the problem is f at x is no longer equal to this. This is how you represent the inverse of f at x, okay? We put a little exponent -1, and that means that's the inverse of our original function, okay?
So you need to get rid of that.
Yeah, essentially what we did is replace the y with that exact there. F
With
to inverse
the-
1. We don't need to get rid of the -1. All that tells us is that is the inverse, bring everything up, of what we started with. We started with f at x, and now the inverse function is what we have here, and we're just going to write that part out now. So, when we go to write this, we're going to start with the -3. And the reason I'm going to start with the -3 is because when we square root something, there's actually 2 answers to it. Okay? When you're finding the square root of a number, you technically find a positive and negative version of that number. An example of that would be like if we were finding the square root of 9. Okay?
Which is both sides of the parabola,
Uh,
like this side and that side.
yeah, you're right. When you're looking at a parabola, you can do it like that. If we're looking for just the square root of 9, most of the times you go with positive 3. 3 times 3 is the square root of 9. But technically, another answer is also -3. Both of these are correct answers because if I were to square either of these, I end up with 9 again. Yeah. So usually what they'll do to represent that we have 2 answers, they'll say it is equal to plus or minus 3. Okay? So because we know we're going to have some number in here, what they've done is represented that already. They're going to put plus or minus whatever this root is. Okay? And then we'd eventually split the equation if we were trying to solve stuff like that. But this is the inverse of that function. This is how you would show it in comparison to the original. Okay? So the inverse of the function is f, the power of -1 at x, and that's the inverse of the function, and this was the original function. So we write it in this notation so that we know that this here, this equation represents the inverse of the original equation.
Okay.
Okay? It's just symbols so that we can recognize. Okay. So now say we want to graph these. Okay. Our original is a quadratic. The next one we have is a root, square root to be exact. Now this here represents how to move any function at all. Okay. So A deals with vertical stretches and compressions. We'll get into it. One of the quick rules is if A is greater than 1, we have a vertical. Move this down a little. We're going to have a vertical stretch, they call it. Okay. If A is a number between 1 and 0, we get a vertical compression. K is the same idea, the only difference is it's horizontal. Okay. Now if K is greater than 1, we get a horizontal compression. We'll talk about exactly what those are in a second. But these are the words that they use. And if K is between 0 and 1, we get a horizontal stretch. same idea again. C deals with translations left and right. Okay, and as a whole, I just want you to think of this as this term here. Think of this as negative C. So when we talk about C, we're going to think about the whole thing in general. I'm going to explain to you why it's kind of backwards the way it is, but we'll, for now, we'll just think of it as the whole thing in general. So if C is a negative number, so if C is equal to negative, then we move in a positive direction. So we move right. And I'm going to say positive direction. So, with that being said, if C was a positive number, what do you think we would do? Yeah, exactly. We'll move the entire function, depending on what it is, left. Negative direction. So it's kind of counterintuitive. And then we have D. D deals with moving the function up and down. But D is exactly the way you would think it would be. If D is a negative number, we move it down, which is a negative direction. Exactly. And if D is positive, move it up in the positive direction. Okay? Now there's a couple other things we need to talk about with this. But what this is because technically I have two different functions here. This is a root and a quadratic. But these rules that they've put here can be applied to either of them. This f here deals with the function itself, or the parent function. So what it's trying to tell you is it doesn't matter what the function is, if you can distinguish what the a variable is, the k, the c, and the d in any of the function, this is how it will affect the original graph. So the original graph of our f at x, or original, is f at x is equal to x squared, which is a normal parabola. We're going to, in a second, show you what that graph looks like. And this one here, our inverse, the normal one for that, is actually just the root of x. Okay? All these other numbers affect it. So what we have here now is a parabola, our original one, which is what we said. This is technically y is equal to x squared. The vertex of this guy is at 0 and 0. Okay? And now if we're trying to figure out how to graph it, because it's squared, what we do is if I were to move to the right one, whatever I move to the right, I square that number. So because I move 1 to the right, I square it. 1 squared is 1. So I now know to move up 1.
Or 2 up, 4 up, or 3 up, 9.
Yes, okay, good. So you know all that. So that's how you graph the original quadratic function, right?
Yeah.
That's what we have there. Now what we're going to do is we're going to see what a root would look like. Okay, and the next thing we've drawn in here is a square root. Now, this is our y is equal the root of x. Remember we said that would be essentially the inverse of it. So if we had f at x, let's write this in permanent here. We had f at x is equal to x squared. That's our top one here. Should have wrote in blue, I guess. But this one here would be the inverse. F at x is equal to the root of x. This is exactly what the graph looks like. Now, technically, because remember we said there's a plus and a minus answer to any root, technically this kind of repeats this down here. It goes like this, and goes down forever. Okay? But the reason they're only drawing half of it is because, I don't know if you remember doing this, functions. A function has to pass something called a vertical line test. And what that is, if I draw a vertical line, it cannot touch the shape more than once. So if we drew it this way, it touches it more than once, okay? Which makes it not a function. So that's why they don't include the bottom part. They only include the top part of this. Okay, so that's what they're talking about. Now, when we talk about shifting the parabola, okay, so let's bring up, remember we had our original. We said f at x. Remember I told you these rules, they tell us how to shift any parabola. X minus plus d. We have our a. Oh, I don't have all the colors here. We'll just have to make two. K, and we'll do, actually let's color code this. We'll do vertical things in black and horizontal things in red. Okay. So, remember I told you that these will affect how our graph looks. So we had actually drawn, or we'd had an original function, f at x, and this f stands for whatever function we're dealing with. So in the first one we're dealing with a square root. We got the number 2, plus, I think it said 3 squared minus 4. Okay. What that is here is our a value. So in this case, a is equal to 2. Okay. And what a is going to do is going to stretch our quadratic vertically. And what we mean by that, remember I said if we go over 1, we square that number, right? And we square it, we go up 1. Well, after I get the amount, because a is a number greater than 1, I now take that number and multiply it by this. So, in other words, what that means is instead of going up 1 times 2 is 2, I will go up 2. So the new guy is going to have a point here. And when I do the same thing to the left, I go in a negative direction. So negative 1 squared is 1. But because a is 2, we multiply that by 2. I go over 1.
Y? Like A is the y-axis?
Yeah, because it's a vertical stretch, so we're going up the y-axis. Okay, that's a vertical stretch. So with that same idea, normally we go over 2. How many do we go up? 4. But because a is 2, we multiply.
Over 2 and up
8, exactly. So we got 4, 5, 6, 7. It doesn't even fit in here. It'd be something like this and like this. That's okay. So we're going to have a parabola that looks more like this. Okay, it's going to be stretched more. And what I mean by that is that's if the function was f at x is equal to just 2x squared. We'll have a thinner parabola. So I'm actually going to put that up here. The good thing about this program is we have so many different colors when we do it. So let's bring that up. Don't need that. Where y is equal to, we said 2x squared. And if you see our green one, like we said, it's been vertically stretched. It's a thinner parabola. And that's when we just had the 2 involved. Okay? But remember, with our function, another thing also happened with it. It was actually f at x was equal to 2x plus 3 squared minus 4. We said that 3 dealt with horizontal shifts. Okay? And now I'm talking about the whole thing in general. So if it's a positive 3, we actually go in the opposite direction. So the green parabola right now is going to shift 1, 2, 3 to the left. And all the points are going to be the exact same. So we're going to have the same.
The vertex is going to be switching?
Oops. Sorry. I don't know what that was. So if you look again, I'm only doing these one at a time. We're eventually going to see the final guy altogether. Okay? So we started with the blue guy. He's the original. Then we went to the green guy. He's been stretched vertically. Then this purplish color, because it was positive 3, the green parabola was shifted to the left 3 in every single point. So it's still the same shape, hasn't been stretched at all. It's just been moved to the left. And finally, we said that the actual function is x plus 3 squared minus 4. So what do you think is going to happen next? It's the last thing we got to add to it.
Add 4 up or downward.
Yeah, so this purple one is actually going to go down 4 units. So we'll bring that in. So if you look now, our final one is the orange guy here. Okay, that's where we had the whole function. So we zoomed out a little. We started with the blue one. It got stretched vertically, so in other words, it got thinner. The positive 3 made us move it 3 to the left. And then finally, the negative 4 made us move the entire parabola down 4. So our actual function is this orange one here. So I'm going to take away all the other guys so that we're just looking at it now. Okay, so now we got rid of all the other ones. So this is the function we were talking about that we just did an inverse to, right? It is represented by what we have up there. I don't need to write it again. Now our inverse was a root function. And remember I showed you a root function. We're going to bring another root up. It has a different shape to it. It's something like this. Okay, and we're going to talk about how it's also affected by those same variables where we had the a function k x minus c plus d. We're going to talk about how it's also affected by those and how it would move that. So here's our root function. Okay, like I said, it looks like this. And we're going to do all of our changes to it. So we had the inverse of the function, which we had when we go to graph it, was negative 3 plus or minus the root of x plus 4 divided by 2. Now, I'm actually going to rearrange this just so it looks a little more like what we had where we had our f at x was equal to a, the function. This is our function. We're dealing with a root function. So we have this, and we're going to move this blue root around the page, depending on what numbers are in place for A.
So it's just gonna end up being.
Yeah, it's probably going to move on. We're going to figure out exactly how it moves by looking exactly what it is. K plus D. Now, if you notice, this 3 is in the front right now. It technically represents our D. So I'm just going to move it to the back. I'm going to rearrange the equation just so it looks a little more similar to this, because this is how we're going to try to guess at what it's going to look like when we move it. And this is actually going to tell us exactly. So I'm going to rearrange the function just a little, and it's going to be plus or minus the root of x plus 4 divided by 2 minus 3. Okay. So right away, that minus 3, because it's D, what do you think is going to happen? We'll get Ketzel. What did D do? Do you remember what it did to our parabola? It had to deal with translating. Yeah, put it down 3. Well, in the other one, you're right, because the number was 4 here. It moved it down 4. In our case here, it's negative 3. So the same idea, it will move this parabola down 3. Okay?
But will it move? Oh, because it's still y, even if it's not.
Yeah, exactly. So what we're going to do is we're going to put that as the very first thing we put into this graph. So we'll make a new one here. So there you go. We take a look. We have our minus 3, and lo and behold, let's get a real point. Here's a point here. We've gone down 1, 2, 3. Same with this point here. 1, 2, 3. So still the same shape. It's just moved down 3. Okay, so that's the first thing we have. The next thing we talked about, the inverse function, was plus or minus the root of x plus 4 divided by 2 minus 3. Okay, so first thing I'm going to do is I'm going to try to separate inside of those brackets a little. Okay, because like I said, we're used to looking at f at x is equal to a, whatever the function is, right? Whether it's parabola or a root, which we're using now, k x plus d. Sorry, x plus c. Your variables are a little different, or your letters a little different than what we're used to. C and d. Okay. So what I'm going to do is I'm going to try to find my x. And what I mean by that is x is essentially, do you remember distributive property? If we have a number here, something like, let's say, 2x plus 3. Distributive property is when I move the 2 into both, so I end up with 2x plus 6, right? The problem is that right now we have something like that. It's a part of the equation, so I can't exactly distinguish what my k is. Okay? So what I want to happen is I want the variable x, like in this case here, to only have the number 1 involved. So I'm going to factor out. Okay? Now in this one here, this can be technically rewritten as x over 2 plus 4 over 2. And with that being said, what I'm going to do is I'm going to factor the 2 out. I'm going to take it out. So essentially it's a half x plus 4. Yeah, we kind of like when we multiply 2 out or divided 2 out. And so I'm going to rewrite this function just a little. So it's going to look like this, just so we can distinguish what our k is. Plus or minus the root of, so our k value is a half x plus 4. So now I can distinguish my k because it's outside of a set of brackets. Okay, plus d. Now what happens with the k, we talked about it deals with horizontal stretches. Where we talked about a stretch the parabola up and down. This gives it a horizontal stretch. And what's funny about k is it's also counterintuitive. Remember when we said a, whatever we went up, we multiplied it by? That's because we multiply by the absolute value of a. When we're moving the graph, we actually multiply by 1 over k. Okay? So what that means is, because this is a half, it's a little confusing. If I put a half in for the k value, so I have 1 over 1 half, that looks a little funny. Really what all you have to do to distinguish this is take the half and invert it. That's what our new number is going to be. So our new number is going to be 2 over 1, or just the number 2. So when they say we have a horizontal stretch by a factor of 2, is each of these points to be horizontally stretched, okay? So we have this point here, it stays the same, but this guy is probably going to move over, he was moving over 1, 2, 3, 4 from before, okay? So his point, let's go back to the original one. The original one was at 1, 2, 3, 4, and 2. We multiply the x value by this 2 now. So now this point is moved over to 8 and 2. Okay? So this red guy, 4, 5, 6, 7, 8, he's now going to change into a function that looks a little thinner. It's going to go like that. Okay? So I know I have a lot on the page. It's about to go away. we're going to bring in that half underneath the root to see exactly how it affects it now. So if you notice, remember we talked about A was the number 2 here, right? So we essentially, what we took is the y values. We had our original 1 and 1, 2 and 4. So we had our original parabola looked like this, right? And when we stretched it with our A value, what we did is this coordinate here is actually 2 and 4. All we did is we took the number 2 and we multiplied it by the y value. So the y value now became 8, so it was way up there. Here we had 1 and 1. I multiplied the y value by 2, becomes 1 and 2. That's the new value. So that's why we had a stretched parabola. It was something like this. It vertically stretched it. Okay. So here, k is a little counterintuitive. It's the opposite. So instead of multiplying our x values by a half, because remember I said k deals with horizontal, we multiply by the x values. We don't multiply by a half, we do the inverse. So the inverse of a half is the number 2. So I took, like for instance, this point here, which was at 4 and -1. I took the x value and multiplied it by the number 2. So 4 times 2 is 8. 1, 2, 3, 5, 6, 7, 8. There's a new coordinate, 8 and -1. It's been horizontally stretched. Yes, sometimes I get the words confused. It's been horizontally stretched. It's been pulled farther that way, this root function. Okay? Because of this half here. Yeah, we're multiplying by the number 2. So like for instance, another point was here, which is right now it's at 1 and -2, right? I take the x value and then multiply by 2. He's now at 2 and -2, which is right there. That's our new one. So that's how we'd stretch it by hand. Now luckily we have this program which is kind of doing it for us, but I just want you to see what the differences are between them. Okay, so that's what that was. It stretched it. Now technically our function, we said, our inverse function, was plus or minus, all right? And remember I factored it a little so it would look like this, x, oh shoot, was it plus 4? Yes, plus 4. Just forgot that for a second. And then minus 3, okay? Now, in terms of our functions again, remember we had f at x equal to a of the function k x minus c plus d. So we pointed out that this was the k value, this was the d value. What do you think this 4 is? The c value, that's right. What did we say about c? It was kind of counterintuitive. What's it going to do?
It's going to reset itself.
Say it again, sorry?
It's going to be, it's going to like cross out itself.
Well, which way does it move the graph? Remember we said that d moved things up and down? So d did up and down movements. So c is the opposite of that. Instead of going up and down, yeah, so it goes left and right. So whatever the number is, we had positive 4. We kind of think it'll do the opposite of that. So instead of going...
Oh, right.
Yeah.
It's the horizontal compression.
Movement, or translation. So which way would I go? If it's positive 4, which direction would I go?
Left.
Yeah. So our purplish one is going to go to the left. 1, 2, 3, 4. So it's going to do something like this. That's messed up. So it's going to make something that looks like that. The whole thing, the purple one, still same shape, but it's been shifted 4 units to the left. Or in other words, like a -4 idea. So let's put that in, see what it does. So now, remember we started at the blue guy. We then went down 3 units to the red one. We then stretched it horizontally. And finally, from the purple to the green, we moved it 4 units to the left. So the green one is our inverse function. This was our inverse function we found. That's the graph of it. And this was the original function we found. So I'm going to take out all of the intermediaries here, and I'm just going to leave the green and the orange guy together. Okay? So let's turn those off for a second. So what we have now are our inverse functions. This was the original. Right? And he's in orange. That's the graph. And the green one is the inverse. And remember we said the inverse of the function is like flipping it on a 45-degree angle. Okay? So this is what the 45-degree angle would be, something like that. Okay? So that's the line cutting it right down the middle on a 45-degree angle. So what they've done is they flipped this page. So this orange guy is now flipped into him. Now normally, because it'd be flipped like that, they would have points about here. and another point here. Something like that. So really, he would look more like this when he's flipped. I'm not the greatest freehander here. Okay. But remember, I told you in order to be a function, it can only have one line. So this program only draws the top line. If you were to actually invert the actual picture of it, it would, it's got to loop a little better. But that would be what it looks like on a 45-degree angle. So that's what an inverse function ends up looking like, especially an inverse of a quadratic. It's going to turn into, well, I guess you could represent or call a sideways parabola. It's the same parabola, just drawn sideways in this case. The one last thing we didn't talk about is if a is equal to a negative number, it flips the parabola. And what I mean by that, I'm just going to draw a quick one here, or not just a parabola, any function on the, so we say flip on x-axis. Okay, and what that means is if I have something that looks like this, this is when, let's say, a is a positive. This is when a is a negative.
And I was getting those two confused. So it's getting negative a's confused with inverting.
And then same thing with k. If k is a negative, it's a flip, but IP on y-axis. Okay. Now I won't show you that with a parabola because if I were to flip this on the y-axis and to flip these around, well, this is a symmetrical shape. I end up with the exact same thing. So it doesn't really affect the quadratic function. But if we're doing a root function, there's going to be a really big difference. Okay, so just quickly put it in here. Remember, a root function kind of looks like this, sideways. This is with if k is positive. A root function would go the other way if k is a negative number. It's flipped on the the y-axis. Okay, so that's what positive and negative k would do to something.